This video marks the first flight of a large cargo drone. After completing the design, fabrication, and assembly, the time has finally come to attempt liftoff. What you're about to see is not time-lapse footage. It's all captured at real speed. Every component was built by hand, and all electronics and structural assembly were personally completed. This project isn't just a hobby, it's a serious challenge to create a fully operational cargo drone. Today is its first true test to verify whether it's actually flight capable. We begin with a tethered hover test to pre-check structural stability, thrust, and sensor response. Then we move on to untethered free flight. I'll admit, I'm a bit nervous, but I'll walk you through everything as it happened. The first phase of the test is a secured flight with a safety tether. This step prevents accidents if the drone suddenly tips or leaps off balance. We carefully check throttle response, vibrations, level stability, and movement across each axis. Seeing the drone pull against the tether during lift is a great visual sign that there's enough thrust margin. In this process, I observe motor responsiveness, changes in noise patterns, and frame vibration. Predictable behavior here is the first step in ensuring system reliability and safe flight. The more stable this looks, the more confidence I gain to proceed with free flight. Before removing the tether, I conduct a final check: battery voltage, center of gravity, arm lock status, signal strength, all verified. Again, I also check environmental conditions: wind level, landing surface status, and surrounding interference. Now the aircraft is fully ready to fly independently. Throttle up, the drone lifts gently and climbs to a stable hover. However, within seconds, the GPS signal becomes unstable, causing minor drift and loss of directional hold. The aircraft repeatedly yaws to recenter itself, and altitude hold is slightly inconsistent. Sensor data was within normal ranges, but electromagnetic noise seemed to degrade GPS reception quality. Visible vibration also suggested it was affecting sensor filtering. Still, overall thrust and control response remained positive. The aircraft landed gently and concluded the flight without any structural damage. This flight meant more than just lifting off. It was a chance to see how the system behaves under real-world conditions. The GPS interference was more severe than expected, and a redesign of shielding is clearly needed. Vibration levels also had a real impact on flight data, and upgrading the frame damping or mounting structure is necessary. The drone's durability was solid. No deformation or component failure occurred. Post-flight log data confirmed that sensor accuracy and responsiveness were still within reliable margins. Based on what I've observed during this flight, it's time to begin the next round of improvements. We'll strengthen the damping system, resolve GPS noise issues, and reinforce the battery mounting. Flight is an ongoing cycle of testing and iteration, striving for that perfect day. Thanks for joining me on this journey. Your feedback keeps me motivated. If this video happens to inspire someone out there, that alone means everything to me. I plan to keep building, testing, and sharing everything I learn along the way. If you found this video useful or interesting, please consider subscribing, liking, and turning on notifications. It truly helps a lot. Thank you so much for watching all the way through. I'll see you again in the next challenge.